Welcome to Pomodoro Joe for Thursday, April 20th, 2023. Today we're doing LeetCode problem 662, maximum width of a binary tree. This is a medium problem. All right, so given the root of a binary tree, return the maximum width of the given tree. The maximum width of a tree is the maximum width among all levels. All right, the width of one level is defined as the length between the end nodes, the leftmost and rightmost non-null nodes, where the null nodes between the end nodes that would be present in a complete binary tree extending down to that level are also counted into the length calculation. It is guaranteed that the answer will fit in the range of a 32-bit signed integer. Okay. So in here we have an example. So the width is going to be, it looks like this should be 4. Yes, it is 4 because we have 1, 2, and then this missing one would be 3, and then 4. All right, let's see here. In this case, I would think we would have 1, 2, and these are going to be missing. Oh man, so I don't know how many that would be. 1, 2, and then looks like 3, 4, 5, 6, 7, and then this 8th one doesn't count. So that should be 7, and it is. All right. Okay. So we'll put 25 minutes on the Pomodoro timer and we will get started. All right, so for this one, we will do a level order traversal. So basically we'll go down one level at a time in our binary tree. And for this, we will use the double buffering technique. So we'll start with some result. We'll set it to 0. We might need to set it to 1 because, let's do our super simple check first actually. If not root, so there's no root node, then we can return 0. Otherwise, our result will start at 1 because our root will count as length 1. Okay, then we'll do some processing, and at the end we will return our result. So the processing, now this, we will do this double buffer technique where we'll have our current level, and that's just going to be a list of all the nodes in our current level. So in this case, just the root node. Then we'll have the next level. And so that's going to be a list of all the nodes that are in the next level. Now we currently don't know what they are, so we'll have an empty list to start with. But we'll go through our current level, we'll grab each node in the current level, and each of its child nodes will become a node in the next level. All right, so this is very similar to like a depth first search or a breadth first search, but in this case, it's a level order traversal. So we'll start with some while loop. So while we still have some nodes in our level, then we'll grab a node. And I'm going to pop 0. So this is going to be basically from left to right. Okay, now if we have a node, then we'll grab its children and we'll put it in the next level. So let's see. And we'll add the left first, and then we'll add the right. All right, now if we don't have a node, do we need to do anything? I think in this case we actually do, because we need to keep track of these missing null nodes. So even though we don't have a node here, we might need to put in some child nodes just to fill out this level. So let's see, if we are missing this node, if we have an example here. Yeah, so in this example, so we go down to 2 and its left node is missing. So in that case, we would have no node here, but we still need to take that missing left node and add 2 missing child nodes to fill in this level. Okay, so let's see. We only want to do that though if we currently have a next level, because we don't want to have any leading empty nodes. If we have a leading none node, that means it's going to be taking up space that we don't really need. So let's check here if we have a next level. Well, now we need to add these 2 empty child nodes. So let's see, next level, append none, and we have to do that twice. So that's the left, and that's the right. Okay, so now we're filling in these levels. When we get to the end, so at some point, our current level will run out, but we don't want to break out of this loop until we're actually done. So let's just check here. If we are out of nodes in our current level, but we do have nodes in the next level. So this is saying if we don't have any nodes in our current level, but we do have nodes in our next level, well, in that case, we'll just swap these out. We'll say our current level becomes the next level, and the next level gets reset to an empty list. So this is a basic level order traversal. We'll go through our current level. We'll build up our next level by taking the child nodes of our current level, putting them into the next level. Then when we run out of nodes in the current level, we'll just swap out the current level for the next level, and we'll reset the next level so we can start filling up the next level. Now, we do need to do something with our result at this point. We might have a new score. So I'm going to have a helper function to score our level. So we'll have a level score. That's going to be equal to, I'll just call it score. And we need to pass in our current level because we've already swapped it for our next level. So then our result will be equal to the max of our result, or this level score. All right. Okay, so this takes care of our basic algorithm. Now we still need to implement this score function. So how does this work? Well, let's put that way up here. All right, so we're going to have some score for a current level. Well, the score is basically we have to find this first node, then we have to count how many nodes are between this first node and the last node. All right, so let's just find a start node index. And we don't know what it is yet, and we'll have an end node index here. Okay, now we have to enumerate our nodes. So for every node in our node, we need to know the index. Or we can just say for index in length, in our range of our length of this current level. Okay, so we're going to go through every node in our current level, and we'll just have to check, is there a real node here? So let's see. If we don't yet have a start, so if our start node index is none, well then this is our first real node, so this becomes our start node. What about the end node? Let's see, this could also potentially be our end node, but then any real node could potentially be our end node. So we can always just set, if we have a node at this index, then that becomes our end node. All right, so now we go through. We're finding the very first index of our very first node, and we're also finding the last index of our last node. Now, the score for this level will be the range between those two. So let's see, we'll return our end node index minus our start node index. But we actually have to add 1, because if these are the same index, let's say they're both index 1. So it starts at index 1, it ends at index 1, but there's one node. If we did this calculation just saying 1 minus 1, we'd get 0. But we have one node, so we always have to add 1 to our calculation. Now this only works if we actually have a node in our current level. So we also have to say, if we have a start node, otherwise we didn't have any nodes and we have to return 0. So this is a little bit complicated. So we're going to calculate a score for our current level, then we'll go through. So let's just break this down. I think this should work, but we have our base case. If we don't have a root, we return 0. If we do have a root, then we'll put it in our current level, and we'll set our next level to an empty list. Then while we still have nodes in our level, we'll grab nodes out, we'll push their child nodes onto our next level, or empty nodes, or none placeholders, into the next level if we don't have a node at this level. Then, if we get to the end of the level, and we have nodes in the next level, then we will actually swap out the current level for the next level and reset the next level. Then we'll calculate the score for this current level and return whichever is or set the result to whichever is greater, the current result or this level score. Now to score the level, we have a separate function. Now we go through every index in our current level. If we have a node at that index, then that's either our start node or our end node or some node in between. So if we don't yet have a start node, then that becomes our start node index right there. If we do have a start node or we don't, it doesn't really matter. No matter what we have at this point, if we have a node, it's potentially the last node we run into, and that could be our end node. So we'll just set our end node to this index. Then once we get to the end, our start node index and our end node index are set. We find the difference between the two. Now we have to add 1 because if they are the same index, that still means we have one node. But we only can do this if we had some start node to begin with. If we didn't have any nodes in this level, then we'll return 0. Whew, that is a lot, but let's see if it works. And let's see, start node is not defined because I have an extra character. All right. Someday I'll make a solution without any typos. Okay, so it works. Let's see if we can pass all of the runtime checks. Oh, and we get a time limit exceeded. We beat 72 out of 114 test cases, so we have a good algorithm, it's just too slow. Let's see what we can do to speed this up. So this can be a little bit slow, so we could move this entire thing down into here. I don't think that's going to help too much. Just saves one function call. This max is a little bit slow, so we could write our own max. What else can we do? One thing we can do, we don't have to pop these out every time. We could actually just go through every node in our level, so we can make this a for loop. Let's do that. That actually might help. So instead of popping these levels out, let's just say for node in level. And everything else remains the same, so we just need to indent this now. So now we're not modifying our level, but that's okay. We don't actually need to keep track of the nodes that we've visited. So we're just going to go for every node in our level. If we have a node, we'll do the same thing we did before. Let's see, at some point, if we don't have a level, that's not going to work. So this is just going to say when we get to the end of the for loop, let's not indent this one then. So if we get to the end of the for loop, if we have a next level, then we'll do all this swapping again, and that should help us a little bit. Let's see if this works. Time limit is still exceeded, so that doesn't actually help us. All right, so I'm going to put it back to the solution that I know works. Okay, so I know this solution works even though it's not necessarily fast enough. Okay, so at this point, we know that this is too slow. This calculation goes through every node and all of these empty nodes to try to find these end and start indices of our nodes. What if we don't actually store these empty nodes? What if we just store our real nodes and store their index along with the node itself? So instead of having something just like root, we would have root, and it is at index 0. Then for every node, we can keep track of the index that it's at, which means that we don't have to run through this whole array to try to find the start and end. We can just look at the first node and the last node in this level and find their index, and just do this calculation based on the index that's stored with the node. So let's do that. So instead of just putting the node, we'll put the node and the index. So let's see, this means that it's not just a node that we're popping out, we're doing a node and an index. All right, and now if we do have a node, then our next index, well, that's going to be, well, let's see, our child node's index will be essentially twice our current node index for the left. This has to do with, I forget the name, but it's, you know, if you look at a tree and the triangles that the tree makes and the indices, so this is index 0, that's root 0. The left is going to be index 0 of the next level, but the right is going to be index 0 plus 1 because it's 1 over from the left. So this is 2 times x, or 2 times 0, and this is 2 times 0 plus 1. Now if you go down this, so this is going to be at index 1 now. So that means that this left one will be index 1. Oh, this would be index 2 because it's 2 times 1 plus 1 is 3. There we go. Yeah, so our next index, so the index for the child of this node, its left will be 2 times its current index. So that's index times 2. And so we'll add that here. And the right one will be the next index plus 1 because it's just 1 more to the right of the left index. Now that does mean that when we get to these none cases, if we don't have a node, we actually don't need to keep track of these empty spaces anymore, so we can get rid of this whole thing. All right. We still have this when we run out of nodes. Then we'll swap the levels and we'll still calculate the level score, but instead of having to do this whole for loop, we'll still have the start and end index. But the start index, well, that's just going to be, let's see, our current level. Let's just find the first node, and since they're all real nodes, we can say index 0. We might need to check if we have a current level though. So let's just say if not current level, return 0. Otherwise, we have some node, so our current level at index 0 will be the start node, that's our very first node, and our current level at index -1, meaning the last node in our current level, well, that's our end node. And then our calculation basically remains the same. All right, let's see if this helps. All right, I need to make these tuples, right? I need an extra set of parentheses here. Same thing here. All right, now let's try that. Complaining about the tuple. Let's see. Oh, because, right, it's not just the node. We have to grab the index for this node. So that's going to be index 1. Okay, so that was my mistake. These are tuples, so what's in the current level is no longer just a node. It's going to be a node and an index. So we're going to grab the first tuple and grab the index out of it. And then we'll grab the last tuple, or the last node, and we'll grab the index out of that. So that should fix it. And we're getting the wrong answer. Let's see, we have double. So we have doubled our answer. How did that happen? All right, so what's going on here? We're basically ending up with double our score. I think what's going on is I'm actually just pushing nodes left and right, even if we don't have a left or right node. So let's just double check. Let's just make sure we have a left and right. So if node.left, then we'll push the left. And if node.right, then we'll push the right. Okay, let's see if that makes a difference. Okay, that was the problem. I was actually pushing on nones, even though I explicitly said I didn't want to do that. So yes, now we're going to check. If we have a left node, then we'll push the left node on, and if we have a right node, then we'll push the right node on. Otherwise, we don't push on any empty nodes. Okay, let's give this a shot and see if we can pass all the tests. And we pass. So we do okay. We beat 40% for runtime, 39% for memory. Not too bad. Let's do a couple quick things here, see if we can speed this up just a little bit. One thing we can do is eliminate this function call. So let's just go back down here and just say, we know we have a next level, so we'll just do this. And in fact, we could probably swap out, well, that's all right. Okay, let's do our own max calculation here. All right. And then we can get rid of this altogether. We don't need this anymore. Makes it a little bit cleaner. Let's see if it still works. Right, this is not called current level. It's called just level at this point. All right. Okay, it works. Let's see if this gives us any boost. A little bit, 54% for runtime, 67% for memory, so not too bad. Now the last thing we could try is going back to do that for loop again. We only have 3 minutes left, so maybe I'll leave that up to you. All right, I think that's it for me. So with this one, you'll do a level order traversal. You'll check to see if your level has a greater width than the current result and return the maximum result. That's pretty much it. All right, hope you enjoyed this. Hope you had fun. Hope you learned something. Hope you can go out and write better code. All right, I'm just going to try this really quick. Okay. See if this makes a difference. Well, that makes a huge difference. All right, so if we do the for loop, instead of doing while and popping nodes out of our level, it makes a huge difference. Now we're getting 81% for runtime, 39% for memory. Okay, now that is it for me. Hope you enjoyed this, hope you had fun, hope you learned something, hope you can go out and write better code.